My name is Sterling Summers, and this is work that I did while I was at Carleton University. It's actually a follow-up for some previous work modeling walking through apertures in an extension I built for Python Actar. I'll start by describing Actar 3D. Actar 3D is an extension for Python Actar that uses the Morse robotic simulator as a 3D environment. It includes a time-synchronized middleware to support time-accurate experiments. I introduced a new camera class for the environment, a humanoid robot, and it introduced an extended visual module and motor module in Python Actar. While the remainder of this talk is centered around my work in affordances in this environment, there's definitely a sales pitch to do here. Robotic simulators make a great environment platform for cognitive modeling. You can choose a level of abstraction, and if you want to model at a high level with semantically labeled environment, then you can do that. But if your interests are at a low level, let's say with computer vision, then there's no reason, in principle anyway, why you cannot model at that level as well. Environments like these have physics engines, kinematic solvers, etc., that really help open the door for cognitive research at the level of robotics. If you're doing driving or flying research, there's also an opportunity to develop embedded and embodied models in those domains as well, as it wouldn't be atypical for a roboticist to do, let's say, drone piloting in a robotics engine like this. But sort of enough of that sales pitch. That's Actar 3D, and what I'm using it for in this talk is to model aperture passage experiments, which in this case means walking through apertures and rotating shoulders as needed. You can see an aperture in the figure, two wall segments separated by space, and a little bonhomme that will walk through the aperture. In this particular image, that bonhomme has its shoulders fully rotated. The term affordance originates with Gibson and, like many terms in the cognitive sciences, has taken on multiple meanings in the multiple subdisciplines, but roughly what Gibson was talking about was that action in the environment need not be modulated through some inference process involving semantically laden representations, but rather arise as a result of an agreement between the capabilities of the agent and properties of the environment. Now, within ecological psychology itself, there are differing ontological commitments about what affordances are or how they're realized. But the point being that affordance research is somewhat incommensurate with an information processing description. So it's no surprise then that there's very little information processing descriptions or models available in the literature. The research in this area starts with a classical paper by Warren and Wang. They had participants of different sizes, small or large, walk through apertures of different widths, walking at different speeds, rotating their shoulders as needed. Now, of course, larger participants rotated their shoulders more than smaller participants, which makes a lot of sense. But importantly, when the aperture's widths are expressed as aperture width to shoulder width ratios, the group differences disappear. That's what is displayed in this figure from their paper shown here on the right. What they are trying to establish, given their theoretical commitment, is the existence of a pi ratio, a ratio between some property of the environment and some property of the agent, a ratio at which there is some qualitative behavioral change, in this case a shoulder rotation. Their claim in this work is that the aperture width to shoulder width ratio modulates rotation. Now, moving on to story mode a little bit. My interests have always been centered on modeling complex tasks in complex environments, and so I built Actar 3D without necessarily having a good idea of what I was going to model. But then once you have your environment, you build your robot or agent and throw it into the 3D environment, and you pick a task and you start modeling that task, in this case, aperture passage with shoulder rotation. And the very first question that comes up already starts to identify where previous research is found wanting. So your agent is there in the environment, but then how does it know if it'll be able to pass through an aperture once it arrives? And how does it even identify an aperture in the first place? So even though these are sort of the first steps in the aperture passage process, they're the kind of details that might be overlooked and have been overlooked in the literature if you're actually not modeling the process. But it's the kind of processes that make your model a non-starter if you don't have them. And so I realized I needed some means of making judgments about passability, not only for the agent's current posture without shoulder rotation, but for some future posture if it should rotate its shoulder when it arrives at the aperture. And these processes are the kind that really haven't been addressed in the related literature. And one way to solve that problem is to propose body schema and memory of body schema. And that the first step in the passability judgment occurs well before the agent has even started the experiment by storing body schema from experience that are later used to or later retrieved during judgment. Then there needs to be a judgment phase of some kind where you compare your stored body schema with the geometric properties of the aperture. Then, when the agent is walking towards the aperture that it is judged to be passable, there needs to be something, a plan, or in this case, a bottom-up trigger that initiates rotation. And then finally, something needs to terminate rotation because when we walk through narrow apertures, we don't always necessarily rotate our shoulders maximally. So I had to develop a model that addresses all these processes. And while I've done that, there are still a lot of experiments to run so that I can validate the solutions that I've proposed. I ended up running a couple of model experiments from Warren and Wang's original paper, mimicking the physical conditions as best I could. So I had small agents and large agents, and those agents walked at speeds according to the descriptions in the paper and walked through apertures, again, according to the description by Warren and Wang. We can see on the right the fit of the model to the human data with the model in color and the human data in grayscale. But more than this particular fit, the point I want to make here is really about the source of the model's predictions. So the model predicts angle rotation at aperture widths in different speed conditions, but the source of those predictions is the temporal dynamics. So while in the ACT-R community, we are often concerned about reaction times or memory effects, here we're interested in how the temporal dynamics of control result in rotations. We're interested really in how the visual system and the production system and the motor system work together temporally, resulting in agent rotation. And of course, part of that mix is the agent size and certain assumptions about kinematics. For example, across the experiments in this paper and in previous papers, I chose a single rotation rate of 120 degrees per second. Now that's a high rotation rate, but there's only one paper that I know of that describes rotation rate at all. So to foreshadow the discussion at the end, there's still some empirical work to do regarding the kinematics that will really help or could really help falsify the model. But all in all, I think the model is in the right ballpark. The areas highlighted in black there are largely areas where the model over rotates. And those start raising questions about the model, like are there assumptions or processes in the model that aren't capturing the human data appropriately, that I'll talk about towards the end. Now, there are a number of studies since the Warren Wang, paper in 1987 that are, in the same general area of aperture passage. Some that, group people together to walk through apertures, people ducking as opposed to rotating their shoulders. There's some really interesting ones in a virtual environment where they modify the visual properties that contribute to the aperture passage judgment. But one that caught my attention, and partly because it's something I could model, uh, at the level that I was modeling, was a study by Higuchi et al. Now, what's particularly interesting about their work is that that is one of the first studies to stray from the original theoretical commitments. What they did was have participants carrying bars of various lengths to modify the effective width of their bodies. And Higuchi et al. Note that by exaggerating the width of the body, if the aperture width to shoulder width ratio is used to modulate rotation, then extremely wide people, i.e. those carrying really long bars, should rotate their shoulders to an extreme degree, well beyond the minimum needs of the task, because rotation is modulated by a multiple of the width. Instead, they proposed that the central nervous system maintains a constant safety margin, that the central nervous system will terminate rotation once a minimum gap between the edge of the aperture and the edge of the agent is achieved. And in fact, this is the way in which my model being presented here differs from a model that I presented previously, rotation termination in the model now computes the absolute difference between the geometric properties of the aperture and the geometric properties of the body schema. So I'm sort of using their idea and incorporating it in my model. To run these experiments, I took the exact same model as the previous study with the exact same parameters, modifying the robot size to match the size of the participants described in this study, and I added a bar for them to carry according to the bar sizes described in the study. Now, if we look at the results of this experiment, in this figure, we're looking at the safety margin between the agent or the bar and the edge of the aperture. Ideally, following their hypothesis, we'd expect to see bars of equal heights all the way across here. Now, they aren't, but they are pretty close. Human data is presented in grayscale and model data is presented in color. The model has a decent fit to human data if you ignore the 2.5 times condition on the extreme right, circled in black. There's a major over rotation there with a large increase in variance as well. Here we're looking at the absolute rotation. The pattern expected is actually exhibited by the human data in grayscale. And again, the model is in the right ballpark, except for the 2.5 times condition on the extreme right, circled in black. And once again, the model is exhibiting an extreme over rotation compared to the human data. So obviously, one of the main setbacks in the model is its over rotation, an example of which is illustrated in the figure on the right that we saw a couple slides ago. And I have no doubt that one of the major components contributing to the over rotation is obviously the high rotation rate of 120 degrees per second, especially in the conditions where the agent is holding a bar that's 2.5 times its width, where even the slightest movement in degrees results in a large movement amplitude at the end of the bar. And it may be that the assumption of an instantaneous rotation velocity may be too simple or not sufficiently accurate for modeling in this experiment. But as a modeler, I have no doubt that a better fit could be achieved. But it seems doing so would ignore the fact that the model is constrained by the physical and kinematic properties of the task. Fitting the data in this case would be missing the point, I think, where the model could be used to drive empirical research, right? In this case, we would want to push empirical research to try and falsify the model. And the rotation in the 2.5 times condition is a good example, because one can reasonably expect that the strategy in this case may be different than the rotation strategies in the other cases, because when you're holding a bar that long, participants may slow down and slow their rotation and attend more to the passing of the edges than they would have in the other conditions. Alternatively, the vision system or the camera used may in the model may be in need of tuning, or as calculations at an obtuse angle like that can be prone to error, which may help explain the increase in variance and the over rotation. But really, the only way to know this and to falsify the model is to run an experiment. And that's really the main point of what I'm doing here. I'm really trying to show how the model could be used to drive future empirical research, which would then lead to refinements of the model, right? I really don't expect that I've introduced all these processes and modules to the architecture and voila, I've hit the nail on the head. I really expect that, this is sort of a first pass that can drive future research. And one final point worth making that's actually thought of by the reviewer was that models like these can be useful for building agents capable of making autonomous action decisions by considering the representations of their body and the kinds of action capabilities that they have. Now, the implementation of body schema for this project I happen to know, is probably a little bit crude, but having a more complex and more complete body representation might be useful, especially in an architecture like ACT-R, where we can really model complex tasks. Thank you.